We created the portable weight sensed countdown timer. I'm Ava Peterson.
I'm Levi Stidham.
And I'm Noah Amack.
So for our project, we created a timer, and the timer must include at least 5-minute and 10-minute settings with the remaining time displayed. The timer must detect an arbitrary object placed on or near the timer and must sound an alarm and stop the countdown when the detected object is removed. We have 7 different engineering requirements. The system must be accurate to a precision of plus or minus 1 second when responding to the removal of the detected object. The system must use connectors for every module used in the timer system, have a power disconnect switch, and not have any exposed conductors. At least 9 out of 10 users will use the timer without needing instructions. The alarm must be 440 hertz plus or minus 1 hertz. The system must include 3 brightness levels that are user selectable. The system will allow users to adjust the volume of the alarm, and the system must be portable by being powered through a portable power supply, removing the need to be plugged into a fixed power source.
So we initially chose the ESP32 as our microcontroller. We hit a lot of roadblocks while working with the ESP32, including the code not working, errors while flashing the code, and there was just a lot less resources online compared to some other ones. So we decided to switch to the Arduino Uno R3. The Arduino was a lot more user-friendly and allowed us to get the code working a lot quicker. There are a lot of inputs and outputs for the Arduino. The whole system is controlled by it. To sufficiently power our system, we chose a 14.8-volt lithium-ion battery. This battery provides enough power to sustain the timer for its maximum setting of 10 minutes while also remaining light enough to keep the system portable. There are 3 user inputs for the system: a potentiometer, a three-position switch, and 2 buttons. The potentiometer allows the user to adjust the volume of the speaker. It is connected between the Arduino and the LM386 audio amplifier, which allows for direct control of the signal before the LM amplifies it. The LM then amplifies the signal, sends it to the speaker, which then plays the alarm sound at 440 hertz. The 3-position switch is a direct input to the Arduino, allowing the user to control the brightness of the 7-segment LED display. The display is connected to the Arduino's SDA and SCL I2C communication pins, along with a 5-volt pin. This setup ensures that the display receives power, it stays synchronized with the Arduino's clock, and allows the Arduino to send digital data for an accurate visual output. The user can also control the amount of time they want the timer to count down from via 2 buttons. Both buttons increment in 5-minute intervals. One button increases time while the other decreases it. To activate the system, an object must be placed on top of the lid, which acts as a platform for the load cell. The load cell then measures the weight by producing a small analog voltage signal. This signal is sent to the HX711 weight amplifier, which then converts the signal into a digital signal that can be read by the Arduino. Now, once the Arduino detects that the load cell has been activated, the timer begins. The visual output from the 7-segment LED display will be the countdown based on the timer selection made by the user. Once the time runs out or the object is removed from the top of the lid, the alarm will sound.
So now I'm going to discuss the code that was used for our project. For the code, I wanted to make sure that our project could do the following: show the time left on the timer via a 7-segment display, take and interpret data from the load cell sensor to tell if an object was present or not, and if not, stop the timer. And I wanted to create buttons that would allow the user to go up or down in 5-minute intervals and have the option of setting the brightness with a 3-position switch. This code was all done via the Arduino IDE. To create the function to determine if a weight was present or not, I first had to calibrate the load cell to the weight of the platform where the object would be placed. To ensure that the load cell was working correctly, I was printing the weight on my computer via the serial monitor. I had a floating variable that was the load threshold to activate the alarm. When the weight on the load cell was greater than the load threshold, the serial monitor prints that a load is detected, and if the countdown is not already running, it would change the value from false to true. Otherwise, no load would be printed via the serial monitor and the countdown running would be false. And that is shown right here. When the alarm reaches 0 minutes and 0 seconds, the countdown running is true. The alarm countdown running is true. The sound alarm function is called. The serial monitor prints a message of alarm for a loop, which starts where a digital high signal is sent to the LM386. Then there is a delay of 1 million divided by 440 microseconds. This gives us the 440 hertz tone that was required by the project brief. This is then repeated with a low signal. To read the input buttons, I use two if statements. The first checks if the button to increment up 5 minutes is low because it's active high. Or excuse me, it's active low. Then increase the alarm by 300 seconds or 5 minutes. If the alarm time is greater than 5,700 seconds or 95 minutes, the alarm resets to 0. There is a 200 millisecond delay for the buttons to depress. The second if statement checks if the decrease button was set to low. Again, it is active low. And then takes the alarm time minus 300 seconds, again 5 minutes, until 0 is reached. And that is shown right here in the function handle button input. To properly display the time, I have two integers, minutes and seconds. Minutes takes the alarm time and divides it by 60 with no remainder. Seconds takes the alarm time and divides it by 60 with remainder. This allows for the minutes and seconds to be calculated respectively. To display the time value, I take the minutes times 100 plus the seconds, which then converts it to a 4-digit format of minute, minute, second, second. And then I pass that to the display function as the variable. To enable the 3 brightness levels, I created a function that is composed of 3 if-else statements. The HT16K33 backpack that controls the 7-segment display has a range of brightness from 0 to 15. I set the up position of the switch to be the brightest. If the switch is in the middle position, it is set to 8 because that is roughly half. And if the switch is in the bottom position, its brightness is set to 3. I didn't want to set the brightness to 0 because I still wanted the timer to be visible. And that is shown here in this function. The first challenge that I came across when bringing all these functions together was that all of the other projects, tutorials, and references that I had found had different baud rates for the devices that communicated via I2C. I found that a baud rate of 1,152,000 was sufficient for all devices. After that, the tricky part was coming up with pin assignments for all the different signals. Now going on to the PCB, the biggest challenge that we had when it came to the PCB was that it took a couple of weeks for it to deliver. So we had to make our PCB design and get it ordered by around week 6. We were still in the middle of designing and creating our whole system when we ran into some huge challenges with the ESP32 that Noah talked about earlier. The code was not working, so we decided to switch to an Arduino Uno R3. The PCB was already ordered and we were too far into the project to create a new PCB and have it arrive on time.
So for our CAD design, I hand measured each individual component, and from there I chose a simple shape like a box to house them all. And in order to get the correct dimensions for the box, I used the width measurement of each component as well as the PCB dimensions. And after taking the measurements into consideration, I added some extra space for wiring and any other connective components we had. I then created respective openings for each component while adding a tolerance of 0.3 to 0.5 millimeter to each. And this helps make sure that all the items fit snugly. And I finalized it by adding 4 holes for screws to secure the lid on. One main setback was that I did have to reprint our enclosure. The first time I printed it, I had every side of the box the same width, and I found that the front side where the openings are was too thick for the potentiometer. There was enough clearance, but there wasn't enough room for fingers to grab and twist it easily. And so I fixed this by making the front side of the box a smaller width than the rest.
Some future considerations that my team has is to design a simpler PCB and order it sooner, so just maybe less components on it. Also, we would like to start some CAD work earlier and have some backup components in case anything happens. The achievements of this project were we established a accurate timer with values displayed on an LED 7-segment display. We had an adjustable LED display brightness controlled via position switch. We had an activatable timer by applying a load to the weight sensor, a steady alarm sound that has an adjustable volume, and we all have a better understanding and increased efficiency in working with KeyCast schematics and the PCB editor. Thank you for watching.